Hi everyone, welcome to lecture 4 of the course ML for core engineering disciplines. In the last lecture we looked at the two different approaches to statistics, which were frequentist statistics and Bayesian statistics, and we also looked at some simple examples, and we then derived Bayes' theorem and showed that how it is useful to analyze probabilities in terms of prior and posterior probabilities as well as the evidential probability and the likelihood function. In today's class we will take a simple example of Bayes' theorem to solidify the concept, and then we will go ahead into a journey of probability and statistics by looking at various continuous and discrete type of probability distributions. So let us get started. So we will look at an example, right. So this is a discussion of Bayes' theorem, and we are looking at an example. In this example, in an ML class, 40% of the students are from a science background, and the remaining from engineering. Okay. So, of the science students, %80 have no prior exposure to ML, and this number is 70% for engineering students. We have to find the probability of a student being from a science background given they have some exposure to ML. Okay. So, this is the question we have to look at, and this is a classic case of application of Bayes' theorem, right, because we have been asked to consider the evidence that they have some exposure to ML, right. So, that is the evidence, right. Given a piece of evidence, we are being asked to find the probability that the student is from a science background, right. So, clearly it is a case of application of Bayes' theorem. Okay. So, let us see how this can be done, right. So, let us define the probability that we have to calculate. We have to calculate the probability that the student is from a science background given they have ML exposure. Okay. So, let us call this as the event A1, and we are doing that because we know that there are two possibilities, either the student is from a science background or they are from an engineering background, right. And let us call this the evidence B, right. We already identified this as the piece of evidence that they have some exposure to ML. So, this is now probability of A1 given B, right. That is what we have to calculate, right. So, knowing this, right, we can straightforwardly apply Bayes' theorem. In the last lecture we learned that when there are multiple events B that can occur, right, then probability of a particular event occurring given the evidential event B can be written as probability of AI times probability of B given AI divided by probability of B, and then the denominator we know is just a sum over all the possibilities, right. So, this can be straightforwardly written as summation over all possible mutually exclusive and exhaustive events P of AJ times P of B given AJ, right. So, this is how we will approach the problem. Okay, so let us move on with this knowledge, right. So, what we need to find out is probability of A1 given B, and that we have written as probability of A1 times probability of B given A1 divided by probability of A1 times probability of B given A1 plus probability of A2 times probability of B given A2, right. Now, we have written down this mathematical expression, but we can clearly see what each of these terms are representing, right. This term we already identified is the probability that the student is from science given they have ML exposure, right, and that is the same term which appears first in the denominator, and this term on the other hand is that the probability of the student being from engineering, right, and this is the probability that they have ML exposure given they are from an engineering background. Right, I wrote this the other way here. So, this should be probability of the student having ML exposure given they are from a science background, and then this is simply the probability that they are from a science background. Okay. So, now that we have identified these terms, we can go back to the problem statement and then look at these probabilities, right. So, 40% of the students are from science, so 60% must be from engineering, and 80% of science students have no prior exposure to ML. So, that would mean that only 20% of science students have prior exposure to ML, and similarly 30% of the engineering students will have prior exposure to ML, right. So, knowing these probabilities, we can go back and insert them into the expression, right. So, probability of A1 is the probability of the student being from a science background, right. So, that is 0.4, right, and then PB is the probability that a science student has exposure to ML, that was 20%, and then we can write down the denominator, that is again 0.4 times 0.2, and the probability that the student is from engineering is 0.6, and the probability that they have ML exposure given they are from engineering is 0.3, right. So, this is the formulation, and using this we can find that probability of A1 given B. So, probability of student being from a science background given they have ML exposure is 0.3077, right. So, 30.77% that is the probability of the student being from a science background if they already have some exposure to ML, right. So, this is a simple application of Bayes theorem, and obviously when there are a lot more different pieces of evidence that can be considered given a feature space, then the complexity of application of Bayes theorem will increase, but hopefully this simple example gives you a feel for how Bayes theorem can be applied. Okay. So, with that let us move forward, right. Like I said at the beginning of the class, we will delve today a little bit into various continuous and discrete probability distribution functions, and more so the continuous ones. So, let us start with the definition of a random variable, right. So, this is something which occurs frequently in the study of probability. So, a random variable is a variable that denotes the outcome of a stochastic experiment. Okay. And like I said, these can be of two types. It can either be a discrete random variable, or you can have a continuous random variable. Right. And this goes back to our discussion of the types of supervised machine learning, right. We learned that you can either want to predict a continuous variable which made your problem a regression problem, or you may have wanted to predict the value of a discrete variable which would have made it a classification problem, right. So, we learned that supervised ML has two types, classification and regression, and similarly a random variable, right, which is the outcome of a stochastic experiment or a probabilistic experiment, can also be of two different types, continuous and discrete, right. Okay. So, now two functions can be associated with a random variable that follows a given probability distribution. Okay. So, these are the probability density function and that is often shortened to PDF, and the cumulative distribution function. Which is shortened to CDF, right. So, these two functions play a very important role in characterizing the properties of random variables and the probability distributions that they follow, right. So, now let us turn our focus to continuous variables. They are quite important in our study, right, because we often want to predict the value of a continuous variable. So, let us focus on continuous random variables. Okay. So, if a continuous random variable x follows a probability distribution with the PDF probability density function f of x, then the probability of x lying in the interval x and x plus an infinitesimal amount dx is given as fx times dx, right, and this follows from the use of the word density, right, in probability density function. When you think of, let us say, the density of water or the density of air, as engineers we must be familiar with this, if you multiply the density by the volume, then you get the total amount. So similarly here, when you multiply the PDF by, right, the extent, right, by which the variable is varying, and in this case the extent is infinitesimal, then fx times dx will give you, right, the probability that x lies in that interval, right. So now we can write this a bit more formally using the p notation that we have used so far. So the probability that your random variable capital X lies between small x and small x plus d of x is given as fx times dx, okay, right. And in fact you can use this, right, to find what fx is, and this is an exercise that you may have done in your undergraduate studies, that you can find fx as probability that x lies, capital X lies between small x and x plus dx divided by d of x. And of course when you actually do this with your data, instead of dx you use a finite but small change in the value of x, that is delta x, and I am sure you must have done this exercise wherein you have a histogram, right, you bin your random variable and then you look at the number of times the random variable occurs in each bin or each interval, right. So that tells you the probability of the random variable lying in that interval, and then you divide it by delta x and you get the probability density function PDF, and then you can plot it as a function of the random variable. So I hope you probably have done this, or if not, then you can treat this as an exercise that you can try for any sort of random variable. Okay, so that is the definition of f of x. Now what we can do is, right, we can integrate this probability, right, because right now it is over an infinitesimal interval, right. So what we have done so far is we have looked at f of x, right, as a function of x, and maybe it looks something like this, right, and this can correspond to a certain distribution. We will learn what that is, but you know what we can do is we can integrate out this, right, over an interval, right. So let us say you integrate this out over this interval, right, from some value a to another value b, right. So let us say this is a and this is b. So if you compute the integral of f of x, right, over this interval, clearly it will denote the probability of capital X lying in that entire interval, right, because you are taking up all the probabilities and then you are adding them up. That is what integration does, right. So it follows that the probability of the random variable capital X lying between two possible values a and b is p of capital X lying between small a and small b is simply the definite integral a to b fx times dx, right. So this is again something that is useful. So, now what we do is we actually define this as the difference in the cumulative distribution function capital F, right, between the values f of b and f of a, right. So, this f is nothing but the cumulative distribution function that we had introduced on the previous page, CDF, right. So, we have defined the cumulative distribution function as the integral, right, of this function fx times dx. So, let us look at formally how it is defined. So, if you consider this a as minus infinity, right, if you look at all the values of x that are lower than b or lower than small x, that leads you to the cumulative distribution function. So, considering a as minus infinity and b as small x, we obtain the CDF. Okay. So, in other words, your probability that the random variable lies between minus infinity and x, and of course, I should not put an equal to sign here. So, minus infinity less than capital X less than equal to x is integral minus infinity to x fx times dx, and this is f of capital X minus f of minus infinity, and this is equal to 0, right. Why? Because there is no possible value of x below minus infinity. Okay. So, therefore, this becomes capital F of x, right. So, the cumulative distribution function is simply the probability that the value of the random variable is less than small x, right. So, I hope this makes it clear what the CDF means, right. So, the CDF gives the probability that the random variable capital X has a value less than or equal to the argument of the CDF. Basically x, right. So, the CDF f x gives the probability that the random variable x has a value less than or equal to small x, right. So, now you can think of what will be the value of f of infinity, right. So, what will be f of infinity? Just like we looked at f of minus infinity and said that it is equal to 0, f of infinity is basically integral minus infinity to infinity f of x dx, and if you think a little bit, you should be able to convince yourself that this will be equal to exactly 1, right. Why? Because the total probability of capital X taking some value should be 1, and of course, here we are assuming that capital X is a real random variable. We are assuming that the values that x can take are only between minus infinity to infinity. So, x can be any value between minus infinity to infinity, or x belongs to the set of real numbers. So, obviously, if you integrate the PDF, right, from minus infinity to infinity, or you write the CDF at infinity, that should be equal to 1, right. So, this is when we are talking about a single random variable, and as we know machine learning and AI deal with several random variables, right. We are talking about several features, right, each of which can take values and then we have measured them. So, they are really all random variables. So, we need a framework to handle multiple variables or multivariate data, right. So, oftentimes in AI and ML especially, right, we deal with many more variables. Okay. So, then we have to look at something called a joint probability distribution function, right. So, in such cases of multiple random variables, one can define the joint probability density function. Okay, JDF, right, that is how it is abbreviated. So, if you consider for example 2 random variables, right, then you can look at the probability of each of them lying in a certain range. Okay. So, you will look at the probability of the random variable, first one let us say x, of x lying between a and b, and then the second random variable let us denote it as capital Y, that lying between c and d, that is simply given as the integral a to b and integral c to d of this joint probability density function, which is now going to be taking 2 arguments, because there are 2 random variables f x y dy dx. Okay. And this is basically the joint probability density function. Okay. So, I hope that makes sense, and then clearly we can further simplify this. This is basically f of x y, if we defined a cumulative probability density function of y going from c to d, and then the outer limit x going from a to b, right. So, this would become f of x comma d minus f of x comma c, and then you would also have to put in the limits for x. So, that will simply become f of capital F of b d minus capital F of a d, right, then plus f of b c minus f of a c. So, here f x y is called the joint cumulative distribution function. Okay. So, in notational terms f of x y is simply the probability that your random number x, random variable x is lower than small x, and your random variable capital Y is less than or equal to lowercase y, right. Now, if your x and y are independent random variables, just like you can multiply the probabilities of independent events, you can multiply the probability density functions of independent random variables to get the joint probability density function. So, f of x y x comma y is equal to the probability density function of the random variable capital X times the probability density function of the random variable capital Y, where I am using the subscripts to denote the random variable under consideration, right. And finally, given the joint cumulative distribution function, the joint CDF, one can obtain the PDF by computing the derivative, right, and that could be the partial derivative or the complete derivative, right, depending on whether it is a joint CDF or it is a just a CDF for a single variable. So, for example, for a single variable, right, your f is basically dfx by dx, right, and this can be clearly gleaned from this expression here, right. So, we had defined that the expression for capital F, where was it, yeah. So, this is the expression for capital F. If you take the derivative, you see that small f is basically d of capital F by d of x, and similarly if you had a joint density function f x, then f of x would be del f x y x comma infinity del x, right. So, with that we will finish the first the fourth lecture of this particular NPTEL course, and the next time we will look at various different probability distributions, and we will look at the underlying PDFs and CDFs to give us a feel for how they look, right. Thank you, and I will see you in the next lecture.